Before we delve into the technical breakdown, it's important to emphasize that this is a genuine thermodynamic system, not a speculative device defying scientific principles. The baby Gigafactory X4 operates as a real heat engine, harnessing low-grade waste heat, typically expelled by data centers, and converting it into electricity using liquid nitrogen and advanced superconducting technology. The process not only produces usable energy but also enhances passive cooling for data centers, strictly adhering to the laws of energy conservation and thermodynamics. Exact design specification, 3D model walkthrough. Air intake. Nitrogen, making up 78% of our atmosphere, is both abundant and inert. As a gas, it acts as an effective insulator against thermal and electrical loads, and due to its stability, it's ideal for this application. LN2 generator, dry air scrubber, PSA membrane, and cryo pump. The dry air scrubber eliminates moisture from incoming air, sending it through a pressure swing absorption, PSA, membrane to isolate pure, dry nitrogen. A cryogenic pump then uses this nitrogen gas, recirculating the expanded gas channel into the LN2 reserve tank, making the system highly efficient by reusing the returning cold gas. LN2 storage tank. This reservoir supplies cryogenic liquid nitrogen to the high-temperature superconductor, HTS, bearings and Rebco windings. As nitrogen expands, gases build up and exit through the top outlet, initiating the N2 expansion cycle. LN2 channel. A large LN2 channel delivers cryogenic fluid to two critical components, HTS-MHD magnetic bearings, which eliminate mechanical friction, and Rebco stator windings, achieving near-perfect electrical efficiency. Any system heat causes LN2 evaporation, and the nitrogen gas naturally flows to the lowest pressure point, maintaining equilibrium. N2 expansion starting outlet. All expanded nitrogen accumulates at the lowest pressure point, marking the beginning of its expansion journey through the system. Heat exchange outer housing. This involves two stages, a heat exchanger for the N2 expansion channel, and a waste heat radiator drawing from data centers or other sources. The design maximizes the 1:694 expansion ratio of nitrogen, driving the turbine efficiently while protecting the rotor from extreme cold. N2 expansion channel nozzle jet manifold. The pressurized, preheated nitrogen is expelled through a nozzle jet manifold, applying direct and even force to the turbine or rotor. Magnetic flux pinned turbine rotor. The rotor is magnetically confined by YBCO-HTS bulk pucks and opposing Rebco stator windings. This design enables zero mechanical friction and no physical connection, allowing for extremely high RPM and scalable electrical output. Rebco winding stator cryo Rebco housing LN2 supply. The Rebco stator windings are continuously cooled with LN2, ensuring maximal electrical conductivity. These windings interact with the spinning rotor fields, enhancing ionization and reducing energy barriers. Magnetohydrodynamics, MHD, electron harvester. The MHD Faraday cage harvester extracts electrons from the ionized nitrogen, which becomes a cold plasma in the alternating magnetic fields. The high rotor speed increases electron harvest, yielding additional electricity. While using alternating fields to ionize nitrogen has been studied since the 1960s in plasma research, here we generate those dense alternating magnetic fields naturally through the combination of ultra-high rotor speeds and the strong opposing fields from the ReBCO stators. The mechanical shear from the spinning rotor adds to the ionization effect. The MHD Faraday cage then serves a dual purpose. It acts as active arcing mitigation by continuously extracting free electrons before they can build up and cause discharges, while also harvesting them as additional electrical output from the resulting cold plasma. YBCO Type 2 HTS. YBCO HTS Type 2 puck bearings are exceptionally efficient at trapping and repelling magnetic fields, allowing the rotor to be flux pinned without physical contact, meaning effectively 0% mechanical friction or connection to the spinning rotor. N2 expansion channel, heat exchanger intake. The low-pressure outlet feeds expanded nitrogen into a heat exchanger, where it begins to condense as it loses thermal energy to the LN2 reservoir. N2 expansion channel, heat exchanger, cold to hot. Waste heat from auxiliary sources is directed here, further accelerating the nitrogen before it reaches the nozzle jet manifold. N2 expansion channel return, end module. The module's end returns expanded nitrogen to the heat exchanger, closing the loop. N2 expansion channel heat exchanger, hot to cold. Thermally loaded nitrogen passes through LN2 pre-cooling, reducing energy costs for the LN2 generator. Pre-cooled N2, LN2 generator intake. The cycle's end returns pre-cooled nitrogen to the LN2 generator intake. Thanks to the Joule-Thomson effect and the cold reservoir, the system recirculates nitrogen with up to 95% efficiency. Power output manifold. Power generated from Rebco stators and MHD harvesters is channeled, alongside LN2 for passive cooling, to the battery or energy storage unit. Battery energy storage AI compute manifold. All generated power is stored here, alongside computer hardware for AI system monitoring, both benefiting from passive LN2 cooling. Auxiliary waste heat input. Waste heat sources such as data centers, power transformers, and air conditioning units feed into the system. This not only turns otherwise wasted energy into useful power but also provides enhanced cooling, improving operational efficiency at the source and transforming a cooling penalty into a practical advantage. In summary, the Baby Gigafactory X4 is a novel, scientifically sound system that leverages waste heat and liquid nitrogen for efficient electricity generation and improved cooling, all within the bounds of established physical laws. So in simple terms, ambient air is turned into LN2, which cools the superconductors, evaporates into gas, gets preheated by waste heat, expands powerfully through the nozzles to spin the frictionless high RPM rotor, generates electricity in the stators and MHD harvester, then returns to be recondensed. Waste heat in, clean power out, plus free cooling as a bonus, for compact modules sharing one LN2 tank, grounded in real physics and ready for prototyping.